What was the hardest thing in this riddle for you?
Yeah, getting the data right for the cube. So this is hard to picture in the head, and I still not able to do this. So I had to build this paper thing and looked on it how it works.
So, welcome to Advent of Code of day 22. This riddle is a little bit hard, so we just present the solution and explanation, and Frank will do this. Hello, Frank. Thank you that you explain us the solution of riddle day 22.
Hello, Thomas. Yeah, today 22, the monkey map. So this is a bit complicated to implement because it's in 3 dimensions again, but the first star is only in 2 dimensions, so it's a bit less complicated. So I will in short explain the problem. We get as input such a map with obstacles in it, and then the funny thing is in this map there are also like void positions marked as with spaces. And now in the text, it turns out that these space positions are kind of jump over. So if the world wraps around like in Pac-Man, but if you go out here on the right end, then you jump over all these spaces and go left into the world again, where there are real signs here. So, and then these crosses are obstacles. So if you move in some direction and go against such an obstacle, you simply stop. These are the rules. And then you are getting such a path here. In the original problem, it's like 4 kilobyte of path. And then you only have to execute these commands. So step 10 steps, turn to the right, step 5 steps, turn to the left, and so on. And then the question finally asked basically, at which position are you when you have gone all this path? So the first step, what can go wrong is here that the parser, I did simply parse it by lines and then appended these spaces to the end of the lines where they are missing so that all lines have the same size. So I end up with a 2-dimensional arrays of chars here. And then I can walk in this thing. And then I'm parsing, of course, the path. And then I simulate this iteration. I always have a current direction. And then I simply go into these simple steps. And this is basically my loop that makes this. So it goes for the path.size, so each one token is 1 step. And then I check if it's turn right, then I change the direction to the right and else to the left. And else I get this value, this number of steps. So here it would be a 10 because it's a 10 in path. And then I do these 10 steps.
So
then
just repeat for me. You go 10 steps or you get directly into an obstacle. Then you stop, maybe after 3 steps.
Actually, I do 10 times a step by 1. And after each step, I check this obstacle, but I will explain. So the first thing is we calculate the next position after having this 1 step. This is more or less simple. We add this
the directions.
Yeah, this delta of the directions. And then we check if we below 0, then we did go of the left side off. If it's more than n, so in this case 50, then we go out of the right side. And if this happens, I just wrap around. So, and then I also check if there's an obstacle. If there is an obstacle on the new position, I actually go 1 step back. I memorize here the previous position and just break this loop. So I stop here. And then what I also do is if I'm on a space field, then I simply do it again. So here's a do while I'm on spaces. So this means if I go, for example, right here, 1 position, then I'm on a space, and this while loop comes into play, and I go left, right, until I go against the obstacle, and then I notice it's the obstacle, and I jump back to the original field. So, and actually this works. So this
very easy, cool.
My variables here, I call them II and JJ for some reason. In the end, show the correct values, and then we have to do such a multiplication here with some values and can output this. And this works more or less fine. So the most difficult part here was to handle these spaces correctly and parse the input correctly, that the line ends are long enough, because we have to cut out the new lines at the end of the lines and things like this. So, but once we get this right, then it works. Yeah.
Okay.
So this was the first star. So then the second star gets kind of complicated. So the second star, we notice that our grid is actually a cube, and this cube folded, so cut on the sides and then folded and put on as a map on the table. So what we now have to do is to fold it back into a real cube and then think about it. So for example, if you are here on the side 1 and you go left, then you come in on the side 3 here. So if you're in the second column, you come here back. No, if you are here in the second row, you come here to the second column and go left, and then you go down here because it's folded. So what I actually did is I cut it out on paper and put it together for me.
Can you hold it a little bit up? More
up?
I
hold it into the camera, but I guess.
No, it's not yet. No, it's it's the camera. Yes. Okay.
Yeah.
So you. Okay. Play with paper.
So it's not visible nicely here, but one can imagine this. So just cut out this map and fold it together, then you got a cube in your hand. So what I then did is actually I marked the upper left corner on every piece. So, and then if I fold it together, these sides get kind of rotated if they put together. So one can imagine this here, if the side 1 and the side 3 comes together, then the side 1 gets folded 1 to the left, so it's get rotated one position or the one direction to the left, or we can imagine the side 3 gets rotated to the right. So once we got these rotations, we see these rotations, we can use these rotations to make everything simpler. So it's actually, I made for myself here such a matrix of rotations. This is rotation x, mn is the number of rotations of n to the right if going from m to n. So if we go from side 0 to side 1, we get, or from side 0 to the 6 other sides, we get these rotation. I mark the ones that do not exist with a -1. So from a side, you cannot go to itself and you cannot go to the opposite side of the cube, only the 4 other sides. And this are the numbers of rotations you do on the new side if you go off this side. So I type this by hand, clumsy, try to figure it out on the paper piece, and then you end up with such a matrix.
So
and then,
for me, if you go from the first side to second side, you do not rotate because there's a 0, right?
Actually, then I do not rotate the second side. Yes. The numbers are not these ones from the example. It's from the real input, and there are the sides other than here. So if I would go here from 1 to 2, I actually would rotate.
Yes.
So it is simply that the map looks otherwise than in the original.
But in the same row, also side 2, side 3, and side 4, if you switch between these sides, you don't have to rotate.
Yeah, actually. So here, for example, is the side 4 in my thing, and if I go from side 4 to side 3, there's no rotation because they are in the same rotation on the original map for some reason. So some sides simply are on the same rotation. So, and these rotations are fairly small number because 4 rotations is a full rotation, and then so it's mod 4. So this is one thing. So I can translate now my single sides of the cube, and I have a normalized size. So I know one orientation is this, what I originally have. So now what I also did is
sorry for the second question. So 1 is rotate clockwise and -1 is rotate counterclockwise?
No, it's always rotate clockwise. I only rotate right. -1 is the sides that do not exist. So
I forgot. Yeah. Yes, okay. -1 not exist because they are opposite together.
Yeah, exactly. So now I have the adjacent side. So this is, if I'm on the side 0, I can go to side 1, 2, and 1, 2, 3, and 5. If I'm on the side 1, I can go to 4, 2, 0, and 5, and so on.
Okay.
And this also is in the right direction. So if I go from the 0 side to the right, I end up on the side 1. If I go down, I end up to the side 2. If I go left, I end up on the side 3. And if I go up, I end up on the side 5. So I also did this for all 6 sides in all 4 directions, which is also clumsy, and I needed a paper for this, and I don't know, half an hour time until this was right. But then I can, once my side is rotated in the right direction, I know from the current direction what is the next side I will end up. So, and then I can take the next side and rotate it according to my rotation matrix so that it fits to my current side. So now with these 2 matrices, I can kind of simplify my running action. So the vectors for +1 and -1 stays the same as in the first riddle. And then I created a function which is called normalize. So this normalize function gets a current side and then rotates it until it's in the original position, and also rotates the current direction, and also rotates the current point where I am currently. So it rotates all of the system until it fits to the thing like it is in the 2D map.
Okay.
So and then what I do with this thing is actually whenever I'm in this position, so changing direction stays the same as before, but if I now have to do steps, I first normalize my current side. I normalize my whole grid so that it looks like in the original picture.
Okay.
So this includes that I rotate the current side. I actually do this in the strings. I copy the charts from one rotation to the others, 2,500 per rotation, but it doesn't matter. It's fast enough. So then the current direction is rotated and the current position is rotated. And then I do assertions here to make sure that it actually works. And then I can simply step. And then I take here from my current direction and the current side I'm on, I'm finding the next side, then I normalize the next side also for some reason, and then I simply do the steps, rotate it according to my rotation matrix, and then actually it works.
Okay, cool.
And then after all, I got a kind of target position found, and on the last side I again normalize this to the original thing, and then actually the result comes out in the right thing. So this with the rotation makes it kind of not so difficult, because we only need this rotation matrix and this agency matrix. So another solution would be to not rotate the sides, but instead rotate the position and the direction where you are off.
Yeah.
But with this other solution, you would have to consider 24 cases. This is, from each side, you have 4 possible other sides you can go to. And 6 sides times 4 directions is 24 cases. And for each one of this case, the direction changes in a special manner, and the coordinates change in a special manner, and the rob around where you go from left to the right and so on changes in a special measure. And this is very complicated than otherwise. So I choose this solution, and it was actually horrible complicated to get it right, but in the end it worked. Quite happy to get rid of this riddle.
Do you like this riddle?
It was fun to implement somehow, but somehow there was no deep insight here. There was not too much to learn. It's more like an testing of intelligence and awakeness, something like this. It's not real programmers' work doing things like this.
What was the hardest thing in this riddle for you?
Yeah, getting the data right for the cube. So this is hard to picture in the the head, and I'm still not able to do this. So I had to build this paper thing and looked on it how it works.
I like that you use paper and scissors to solve this riddle. So you combine an old riddle where you have stone, paper, and scissor with this riddle. Fine. Frank, congratulations. Big thank you to you. Something else you have to talk about?
No, everything is fine. We will see tomorrow for the next riddle.
Then We see us tomorrow. Much luck. Have a nice day. Bye-bye.
Have a nice day. Goodbye.